So today we are going to discuss about Fourier series and harmonic analysis. Okay, any periodic function can be represented by a Fourier series. Okay. Provided it satisfies the following condition. Okay, so what's the first condition? It should have a finite extreme. It should have a finite extreme. By that mean it should have a finite amplitude. The amplitude of the periodic function. What is a periodic function? Any function which repeats itself after a particular period of time. Okay, so if this x-axis is the time axis and this is the amplitude, then any function which repeats itself after a particular interval of time, right? So this is the time period of the function and this is the amplitude. Okay, and it should have a, so any periodic function, any function of this kind this kind of function can be represented by a Fourier series, provided it obeys the following condition, like it should have a finite extrema. The integral over this function between this period should be integrable. Okay, this function should be integrable between this time period. Okay, absolute integrable over a period. Okay, it should have an absolute integrable over the period. Okay, and the third condition is it should have a finite discontinuity and as only finite discontinuity. Okay. I'll explain this point as we go on, but for this time just take this as the message. So any periodic function, it doesn't mean it should be a cos or a sine. Any periodic function can be represented by a Fourier series, provided these three conditions are satisfied, right? Okay. So what's the Fourier series of a function? So Fourier series of a function f of x can be written as f of x equals to a0 by 2, where this is the DC part, this is called DC part. Okay, this is the DC part, plus summation n equals 1 to some finite value p an cos nx plus summation n equal to 1 to p bn sin nx, right? So this is the Fourier series form of a function f of x, right? Okay. So this is the DC component. Here a1 and b1 or the fundamental frequency, here we have a1 now. If the limit runs from n equal to 1 to p, then a1 and b1, there will be a1 and b1. This a1 and b1 are called the fundamental frequency. And all other values of a and b, that is a2, a3, etc., and B2, B3, etc. are called the harmonics, right? So they are called the harmonics. So let me write down the explicit form of A0, An and Bn so that we can represent any function, periodic function, provided they satisfy the above three conditions in Fourier series, right? Okay. Therefore, the form of A0 is 1 by pi integral 0 to 2 pi f of x dx, right? And An equals to 1 by pi integral 0 to 2 pi f of x cos nx dx, and Bn equals to integral 1 by pi integral 0 to 2 pi f of x sin nx dx. Okay, so these are the three this A0, An and Bn. These are the things we have to evaluate to write any function f of x in the Fourier series form. Okay, in the Fourier series form we need to find all these An, A0, An and Bn. So before going further, let me write some of the important formulas which repeats again and again while solving this integrals. Okay, so these are the important integrals you should memorize because they are very useful for evaluating this integral. Okay, so let me write down some of the important integrals. So first one is integral 0 to 2 pi. So remember the limit is from 0 to 2 pi. Okay, it's the time period is 2t here. Okay, in all of Fourier transform, the period is assumed to be 2t. Okay, so integral 0 to pi sin nx dx. Okay, it's 0. Okay, and the second thing is integral 0 to 2 pi cos nx dx equal to 0. So whenever you encounter this integral, you can directly write it as 0 because the integral is already worked out to be 0. Okay, so the third integral is integral 0 to 2 pi sin square nx dx equals to pi. Okay, similarly the fourth one, integral 0 to 2 pi cos square nx dx equals to pi. Okay, so you no need to integrate this one. Whenever you encounter this integral or this integral, you can write it as pi. Okay, and the fifth integral is integral 0 to 2 pi sin nx sin mx dx equals to 0. And the sixth one, integral 0 to 2 pi cos nx cos mx dx equals to 0. The seventh one is integral 0 to 2 pi sin nx cos mx dx equals to 0. And the final integral is the eighth one, integral 0 to 2 pi sin nx cos sin x dx equals to 0. Okay, so these are some of the important integrals we encounter again and again. Apart from this, we will also come across this integral very frequently. That is integral of the form u dv, right? So what's the form for integral u dv? It's uv minus integral v du. So whenever you come across the integral of this form, integral u dv, you have to choose u and d by yourself. So there is a trick to find to choose which of the two functions as u. Okay, so the rule is it is called, so let me write shortcut for choosing u for the integral u dv. Okay, so this is the shortcut. You can remember it as late L I A T E. Okay, so this is the order. So whenever you encounter integral of the form u dv, you first try to choose the log 1, okay, as the log 1 as the u. Okay, if you don't have log, then the second important should be shifted to, if you find any inverse, then you should choose inverse. Okay, you may have an inverse and an algebraic form. This is an algebraic form, so you should try to choose u as the inverse one. Okay, you try to choose we can apply this as we move on with the examples, but before that you try to remember this formula. Okay, so the first priority goes to the log function, second the inverse function, the third one is algebraic form, the fourth one is trigonometric, and finally you can choose exponential. Right, so this is the order you should choose. You should remember to choose u for evaluating integral u dv. Okay, so let me work out some examples so you can understand all this application of this formula. Okay, so the example is find the Fourier series for the function. Find the Fourier series. So this is example 1, right? So I can't write here. So let me try to move on this. So the example 1. Okay, find the Fourier series for the function f of x equals to x, and it's in the time, and its interval is 0 less than x less than 2 pi. Okay, so remember, sometimes you will be given 0 to 2 pi. Okay, or you can be given minus pi less than x less than pi, and also we can do all these things as we move on. So just remember, the Fourier function is defined for the period from 0 to 2 pi. Okay, so if whenever you have 0 to pi, then there is a different formula, but it's not very different from the one which I written down in the previous session. So you just remember it is from 0 to 2 pi. Okay, if you encounter 0 to pi, then it's a Fourier of series. Okay, so this is a Fourier series. So what we know that we can write f of x as a naught by 2 plus, let me explicitly write that summation as a1 cos nx plus a2 cos nx, sorry, it should be cos 1x and cos 2x, okay, plus etc. Similarly we have plus b1 sin 1x plus b2 sin 2x plus etc. So if you are wondering where this is coming from, it is just our function as we return as f of x equal to a naught by 2 plus summation n equals to 1 to p an cos nx plus summation n equal to 1 to p bn sin nx, right? So I have substituted this value of n in the summation and expanded it, okay? So that's why we are having this one. So we are going to write this f of x, this x, in this form, okay? For that we have to find our a naught. So we have to find a naught, an and bn, right? Then only we can write this in this form, okay? So to find a naught, we know the formula a naught equal to 1 by pi integral 0 to 2 pi f of x dx, okay? This f of x is the given function, okay? So if we substitute the f of x, we have 1 by pi integral 0 to 2 pi x dx, and this can be written as 1 by pi x square by 2 from 0 to 2 pi. Therefore we have a naught equals to 2 pi, right? Okay, so next we can want to find an, okay? So an equal to 1 by pi integral 0 to 2 pi f of x cos nx dx, right? Okay, so if we substitute the f of x, we have 1 by pi integral 0 to 2 pi x cos nx dx, right? Here we encounter the form of integral u, so it's a form of, so this x is in both as a multiple as well as the derivative form, okay? So it is of the form integral u dv, okay? So in this we have to separate the u, separate u and v, okay? So we have this one, okay? So we can either choose this x as u or this cos nx as u, okay? But the choice is we have to choose is according to our light law, okay? So if we apply this law, then we can choose this x as the u, okay? So we are choosing x because it is of algebraic form. So algebraic form is more prior than trigonometric form. Therefore we are choosing u as x and dv as cos nx dx, okay? So what is du? So du is obviously dx, and we have to find, in order to evaluate this integral u dv, we need v, okay? uv minus integral v du, okay? So we have u, no problem, we have to find v, okay? But we have only dv. So what is v? Therefore v is integral cos nx dx, right? So what is cos nx? It's nothing but sin nx by n. Okay, so our v is sin nx by n. So we have u v, so that we can represent this function as, so this is of the form, so this is of the form u dv, right? So it is integral u dv. So we are going to write this integral u dv as, so our 1 by pi integral 0 to 2 pi x cos nx dx equal to, so it is of the form u dv, so we have to write it as uv. So what is u? So it is x, and v is sin nx by n. Okay, so it is uv minus integral 0 to 2 pi, here also we have integral 0 to 2 pi, right, minus integral b du. So it is sin nx by n into du. Du is dx, right? So you can write this as 1 by pi. We can substitute the limit later after evaluating this integral. So we have x sin nx by n, limit 0 to 2 pi, and minus this integral is nothing but we can take this n outside because it is not a function of x. So integral of, so we left with integral of sin nx dx. Integral of sin nx dx is nothing but minus cos nx by n. Okay, and the limit is 0 to 2 pi. So we have 1 by pi. So let's try to substitute the limit. For 0 we have sine of 0 is 0 and x also 0. So for the lower limit is obviously 0, for upper limit also it is 0. So this one is 0 for both upper and lower limit. However, this function, if we substitute this function, we have so if we substitute the upper limit, so this minus of minus becomes plus, so we have 1 by n square, right? 1 by n square. So if we substitute the upper limit, we have cos 2 pi n, right? Okay, and if we substitute the lower limit, we have cos of 0 is 1. So we can take this n square outside, so we have n square pi here, and here we have minus, right? Okay. So here also you have to remember two formulas. So cos of n pi equals to minus 1 whole power n, okay, and the sin n pi equals to 0. Okay, so for all the values of n, for sin we have 0, and for cos, if it is even, we have 1, and if n is odd, we have minus 1. Okay, so here what we have is, okay, we have cos 2 times n pi, okay, minus 1. Okay, since this is multiplied by 2 for all powers of n, so it's nothing but it's 2n, right? So 2n. So yeah, for both, for n equal to odd and even, we have even powers of n here. Therefore, it is always even. So what's this one? It's nothing but cos. So this can be written as cos 2n. Okay, 2n pi equals to minus 1 whole power 2n. Okay, so for all values of n, we have only even powers, so this is always 1. Okay, therefore we have 1 by n square, 1 minus pi. Okay, here also pi, 1 minus 1, so this 0. So our an equals to 0. So similarly, we have to find bn. So to find bn, we have bn equals to 1 by pi integral 0 to 2 pi f of x sin nx dx. So it is 1 by pi integral 0 to 2 pi x sin nx dx. Here also we have the integral of the form u dv. So it is u dv. So we choose x equal to, so we choose u equal to x. Therefore we have du equal to dx, and we choose dv equal to sin nx dx. Therefore v equals to integral of sin nx dx, and it is equals to minus cos nx by n. Okay, so we have all the contents for the integral u dv. So integral, so this integral can be represented as integral u dv. So we have 1 by pi integral 0 to 2 pi x sin nx dx equals to so it's uv. Therefore we have 1 by pi x into minus cos nx by n plus integral v du. It's nothing but, I didn't evaluate, you try to evaluate. I will write the direct answer. We have 1 by n square sin nx. So the limit is 0 to 2 pi, right? So upon substituting, we have this term is entirely 0 for both values of, for both upper and lower limit. Therefore we have 1 by pi. So if we substitute, we have 2 pi by n. Okay, into minus 1. So it is minus 2 by n, right? So our bn equals to minus 2 by n. So we know an, bn and a naught. So we can substitute this in the Fourier series expression and find the Fourier series of the function. Okay, So let me do that. So we have found that a0 equal to 2 pi, an equals to 0 and bn equals to minus 2 by n, right? Okay. So we know our Fourier series f of x equals to a0 by 2 plus summation n equals to 1 to p an cos nx plus summation n equals to 1 to p bn sin nx, right? So in our case, since an equals to 0, this term is 0, therefore we have, so instead of a0 we have to put a 2 pi by 2 plus, instead of bn we have minus 2 by n. So let me take this 2 outside. So if we substitute this here, we have minus 2 summation n equals to 1 to p sin nx by n, okay? Because we are substituting bn, okay? If we put bn, it will become minus 2 by n, okay? I am taking this, since it is not, this 2 is a constant one, I am taking this outside. However, this n is not a constant one because it is inside the summation, and the summation is running from n. Therefore, we have to put this n inside, okay? So this is the Fourier transform of our function x, right? So this is the answer. So it is very simple, provided you remember the method to find a0, an, bn. Also you have to remember how to find integral of the form integral u dv, right? Let me move on to the next example. So the next example is, let me write example. So example 2. So they have given the function f of x equals to x plus x square, and they asked to find the Fourier expression for this f of x in the interval minus pi to pi, okay? Here also you have to see it has a period of 2t, okay? So how it is 2t? So we have minus pi to 0, okay? So it is, and from 0 to pi, okay? So the total length is from minus, if you want to find the length, you have to find the magnitude, okay? So you can leave this minus sign. So from minus pi to 0, the length is, so the length is pi, right? We have pi, and here also we have a length of pi. So totally the length is 2 pi, okay? So it is defined in this way, okay? Or it can be from minus pi by 2, x less than equal minus less than x, and x less than pi by 2, okay? So here we have minus pi by 2 to 0, and from 0 to pi by 2. So this is not a 2t length, okay? So it has, so this, its length is pi by 2. Here we have a length of pi by 2. So the total length is pi, right? So this is not an limit of 2t, okay? For that you cannot use the formula I have mentioned earlier. For that we have a slightly different formula, and we can go through it as we move on. So you just remember the period of x should be from, it should have a length of 2t, okay? So that's the thing you have to remember. So, and they also asked to find using this formula, they asked to prove that pi square by 6 using this prove that pi square by 6 equals to 1 plus 1 by 2 square plus 1 by 3 square plus etc. Okay, I am not going to find the explicit a0, an, bn. You have to find by yourself, as we have did it earlier. So we know we just find this a0, and let me write the value of a0 explicitly. So if you evaluate integral 0 to 1 by pi, integral 0 to 2 pi x plus x square, right, dx, so it is equals to 2 pi square by 3, right, and an equals to 1 by pi integral 0 to 2 pi x plus x square cos nx dx. Okay, and it is equals to, we have 4 into minus 1 whole power n divided by n square. Okay, and bn equals to 1 by pi integral 0 to 2 pi x plus x square sin nx dx, which is equals to minus 2 by n minus 1 whole power n. Okay, so we have a0, an, bn. So we can write f of x equals to, so what is a0? A0 is 2 pi square by 3 divided by 2. So we have a0 by 2 plus summation n equals to 1 to p an cos nx plus summation n equals to 1 to p bn sin nx, right? So if we substitute this a0, an and bn, we have, so instead of f of x we can write this f of x as x plus x square, because our f of x is x plus x square. Therefore x plus x square equals to, for a0 we can substitute 2 pi square by 3. So we have, so if we divide by 2, we have pi square by 3, right, and plus instead of an we have instead of an we have to substitute this one, so we can take 4 outside because it's a constant. So we have summation n equals 1 to p minus 1 whole power n by n square cos nx, plus similarly we can write bn as, so if we substitute this in this expression, we have minus 2, which we can take outside, minus 2 summation n equals to 1 to p, and we have minus 1 whole power n divided by n sin nx, right? So this is the one we have. In expansion, we will be having pi square by 3 plus 4 times. So for odd n we have minus 1. So therefore we have minus, for even n we have this minus 1 whole power n becomes a positive thing. So for n equal to 1, we have minus 1 power 1, which is minus 1 divided by 1 cos 1x, right? And plus 1 minus 1 whole power 2 is 1 positive 1 divided by, we have n square and n is 2, therefore we have 2 square cos nx, so n is 2, so we have 2x, right? And for 3 we have minus 1 whole power 3, therefore it's minus 1 divided by 3 square cos 3x plus etc., right? Similarly we have minus 2 times minus sin x plus 1 by 2 sin 2x minus 1 by 3, because for this function we don't have n, we have only we don't have n square, we have only n, therefore it's minus 3 sin 3x plus etc., right? So this is the form. So this is what we have did already, okay? So they asked to prove that 5 square by 6 equals to 1 plus 1 by 2 square plus 1 by 3 square plus etc., okay? For that we have to do two things, okay? We have to substitute x equals to, just substitute x equals to pi in equation, in this equation, okay? Let me name this equation as, so this, let it be 1, let it be 2, okay? So substitute x equal to pi, okay, in equation 2, okay? Upon substitution we have here, this side we have x plus x square, therefore we have pi plus pi square equals to pi square by 3 plus 4 times, so cos pi is 1, right? So cos pi is 1, sorry, cos pi is minus 1, okay? So for odd number of pi, that is for cos 1 pi, cos 3 pi, etc., we have minus 1, okay? Therefore this becomes cos of pi is minus 1, minus of minus 1 is plus 1, 1, right? And cos 2 pi is 1, therefore 1 by 2 square, and this one is plus 1 by 3 square, because cos of 3 pi is minus 1, okay? We have to remember cos n pi equals to minus 1 whole power n, right? For odd we have minus 1, and for even we have positive 1, okay, plus etc., okay? And these sign terms will become entirely 0, okay? Next we have to substitute x equals to minus pi. So before that, let me number this equation as 3, okay? So if we substitute x equal to minus pi in 2, we have minus pi plus pi square equals to pi square by 3 plus 4 times the same thing, okay? 1 plus 1 by 2 square plus 1 by 3 square plus etc. So let me number this as 4. So the next step is, we have to, what we did is we have eliminated this one, okay? So if we have to eliminate this one, for that we have to add equation. So adding equation 3 and 4, Okay, we are adding equation 3 and 4. We have, so this and this get cancelled. We have 2 pi square here, and this one becomes 2 pi square by 3 plus 8 times 1 plus 1 square by 2 plus 3 square plus etc. Right? Okay. So upon rearranging, we will have 6 pi square, right? So we have 6 pi square, sorry, 2 pi square minus 2 pi square by 3 equals to 8 times 1 plus 1 square plus 1 by 3 square plus etc. Therefore we can take this pi square outside, and we have 2 minus 2 by 3 equals to this one. So upon simplification it becomes, so it is 6 minus 2, therefore it's 4 by 3 pi square equals to 8 times 1 plus 1 by 2 square plus 1 by 3 square plus etc. And if we divide by 8 on both sides, we have pi square by 6 equals to 1 plus 1 square, 1 by 2 square plus 1 by 3 square plus etc. So this is what they asked to prove. Okay, so let's move on to the next example. So sometimes you will be asked to find the Fourier series where the function is defined in sub-ranges. Okay, so let me work out this example so you can understand. So it's example 3. So they asked to find the Fourier series for f of x, which is defined as 1 minus 1 for minus pi less than x less than minus pi by 2, and 0 for minus pi by 2 less than x less than pi by 2, and 1 for pi by 2 less than x less than pi. Okay, here also the function ranges from minus pi to pi, but the function has a sub range. Okay, so the total length is, since it is starting from minus pi and ends at pi, the total length is 2 pi, therefore it satisfies the 2p condition. So we can use the same formula, a naught equals to, so before that let me write down the Fourier series form. F of x equals to a naught by 2 plus summation n equals to 1 to p an cos nx plus summation n equals to 1 to p bn sin nx, right? So a naught equals to, as usual, 1 by pi integral 0 to 2 pi f of x dx. Okay, and an equals to 1 by pi integral 0 to 2 pi f of x cos nx dx. Okay, and the bn equals to 1 by pi integral 0 to 2 pi f of x sin nx. So one thing you have to remember is, since f of x has 3 values in this interval, we have to split this this integral into three parts. So therefore we have 1 by pi as common. So from minus pi to pi, so for minus pi to minus pi by 2 we have f of x as minus 1, right? Therefore minus pi to minus pi by 2 we have f of x as minus 1 dx, right? Plus integral minus pi by 2 to plus pi by 2 we have 0 dx plus integral pi by 2 to pi we have f of x as 1 dx, right? So this is the difference. Okay, you have to split the interval. Similarly here also we have 1 by pi integral 1 by pi as common, integral minus pi to minus pi by 2 minus, since f of x is minus 1 in this limit, we have minus cos nx dx plus integral minus pi by 2 to pi by 2 0 dx, right? Plus integral pi by 2 to pi cos nx dx, right? Similarly for this also we have 1 by pi integral minus pi by 2 pi to minus pi by 2 minus sin nx dx plus integral minus pi by 2 to pi by 2 0 dx plus integral pi by 2 to pi sin nx dx. Okay, next we can see odd and even functions. Okay, so the next thing is Fourier transform of odd and even function. Okay, Fourier, to find the Fourier, so it's not Fourier transform, it's Fourier series. Okay, Fourier series of odd and even function. Okay, so here we have to see two things. Okay, if the limit is between from minus pi less than x less than pi, here the length is minus pi to 0 and 0 to pi. Okay, so here we have a pi and here we have a pi, so the total length is 2 pi. Okay, so this satisfies the Fourier series condition. Okay, so if we have a function defined in this limit, then if f of x equals is an odd function, then a naught equals to 0, an equals to 0 and bn equals to 2 by pi integral 0 to pi f of x sin nx dx, right? Okay, so if our Fourier series is defined in this limit, okay, it is not applicable if it is defined from 0 to 2 pi. Okay, if our Fourier function is, if this function f of x is defined in this limit minus pi to x and x to pi, then if f of x is an odd function, then you can straight away find bn, eliminating this a naught and an, because it will eventually becomes 0 in this limit alone. Okay, so similarly for even function, if f of x is even function, then a naught equal to 2 by pi integral 0 to pi f of x dx, an equals to n equals to 2 by pi integral 0 to pi f of x cos nx dx and bn equals to 0. Okay, so if f of x is even and if f of x is defined in the limit minus pi to pi, then you can straight away find a naught and an, and bn will eventually become 0. Okay, these are the 2 points you have to remember. Let me give 2 examples. Okay, so let example I think it's example 4. Okay, so if our f of x equals to x square, okay, and if it is defined in the limit minus pi to pi, so we can apply this rule. Okay, so we cannot apply the rule if x is defined in this limit. Okay, we cannot use even or odd function for this limit. Okay, we can use only for this limit. Okay, it is not possible if it is defined in this limit. Okay, even for both the cases the length is 2 pi, we cannot use this trick if it is defined in this limit. Okay, so if f of x is x square, then we know this, since x square is an even function, we know that we have only an and a naught and an. Okay, so bn is 0. So just find a naught, okay, and an. Okay, similarly, so let me give an example for odd function. If example 5, okay, if f of x equals to x cube, right, and it is defined in the limit minus pi less than x less than pi, then a naught equals to 0, bn equals to 2 by pi integral 0 to pi f of x sin nx dx. Okay, and an equals to 0. So this is the shortcut. So let me recap everything we have seen till now. So if f of x is defined in the limit 0 to 2 pi, then you have to evaluate explicitly a naught, an and bn using the formula given earlier. Okay, if f of x is defined in the limit minus pi by 2 to pi, okay, then check if f of x is odd, just find bn. Okay, if f of x if so it should be okay, if f of x is even, find only a naught and an, right? So if f of x is odd, find only bn. Okay, this is applicable only if f of x is defined in this limit. Okay, so that's the recap. I think I can stop here and we can continue with harmonic analysis in the next video. Okay, thank you.